In this video, we'll cover Gibbs free energy. I'll give you the definition first right away and then explain what that definition means. Gibbs free energy is the amount of energy to drive the reaction forward or reverse spontaneously. In other words, Gibbs free energy will tell us whether the reaction will happen in a forward direction or reverse direction, and if it's going to happen spontaneously and non-spontaneously, and it will have a value and also a sign. Sign, what do I mean by sign? Meaning that there is going to be either a positive value or a negative value. Let's give an example to illustrate what a Gibbs free energy is. So here I have a block of ice, and say this block of ice, which is a solid, is left out there at 50 degrees Celsius. Will it melt? Yeah, 50 degrees Celsius is pretty warm, so it will melt, and that happens naturally. In other words, we can say that this happens spontaneously. So this is a spontaneous reaction. And then let's do another scenario. Here's another scenario where water liquid now is forming into water solid. Okay, and the temperature is not at 50 degrees, but rather at negative 10 degrees Celsius. Would this happen spontaneously? Meaning in nature, will that happen? Yeah, it doesn't require much work. It just happens spontaneously. Now, if we were to go to the other way around, we're in a reverse scenario where liquid now goes back to solid at 50 degrees Celsius. That would be considered non-spontaneous because that wouldn't happen just naturally. It does require some work. And that goes same. For a solid to go back to a liquid, say at negative 10 degrees Celsius, that would be non-spontaneous. So tying in this Gibbs free energy, it shows that for this scenario where it's happening spontaneously, it's going in the forward direction. But at what energy expense? Meaning, what is the value of the energy? Well, that we will go over in a bit. And there's this word free here, Gibbs free energy. Is the energy really free? The answer is no. Energy, it comes from somewhere, whether rearrangement of the molecule causes the energy to release or for energy to be inputted in order for that molecule to move in a certain way. There's no free energy. It always comes from somewhere. So there is a mathematical definition, not just wording, but mathematical definition, because if you look at the wording definition, it says amount of energy, right? So how much energy are we talking about? And we will use this particular equation. Delta G is equal to delta H minus T delta S. And what are these individual mean? Well, that delta S, as we have seen, that's change in entropy. The T is the temperature in Kelvin, and the delta H is enthalpy. And delta G, that's the Gibbs free energy that we've been discussing so far. Here is two distinct example that happens in a spontaneously or a non-spontaneous reaction. So we're going to compare the two and look at the Gibbs free energy. Here is a methane gas and oxygen forming into carbon dioxide and water. This is a spontaneous reaction. So I'm going to off the bat write spontaneous reaction. If you look at in another example on the left, you see these spherical balls, and there, as you drop them, it will slide down, and that happens spontaneously. By gravity, it will pull it downward, right? And that's kind of easy to remember, and that's a spontaneous reaction. Well, what is the value of the delta G? The delta G value will be less than 0. Less than 0, so it will have a negative in value. And in this scenario, it favors the forward directions. Favors the forward direction. And this is a reaction that occurs naturally. All of these guys are represented by the delta G being negative, also known as the exergonic reaction. So if something is a reaction that is exergonic, then it should automatically pop in your head that this is a spontaneous reaction. In the other way, another scenario would be the endergonic reaction, meaning it requires energy for that particular substance to react. For example, here's water forming into hydrogen gas and oxygen. This requires work. Or say you have a spherical ball and you're not trying to roll it down, but rather push it up. So it requires some of your energy to push it back up the hill. Right? So this would be considered to be a non-spontaneous reaction. And on top of that, the delta G would be a positive in value. And it will favor the reverse direction. Favors the reverse direction. Meaning if it were to go into the reverse side, it will become spontaneous. Right now, we're going into a direction where it's non-spontaneous, but the reverse will be a spontaneous. So that's why it favors the reverse. And this is a reaction that does not occur naturally. So it's all of these comparisons are opposite from each other. From if you want to know what kind of reaction would this be, this would be a endergonic reaction. So here exergonic, and this is endergonic reaction. Standard Gibbs free energy is G, and then you see a little knot on the corner. And what does that mean? It just means that it is at a very specific state where there's 1 atm pressure and 25 degrees Celsius or 298.15 Kelvin. At that standard position, what is G naught? Meaning, what is the actual energy that a molecule that contains? Well, if you look in your reference sheet, so I'm going to go to the reference sheet. If you look at this reference sheet, you will see a long list of all of these chemicals with its G naught, the standard Gibbs free energy. So, for example, here is hydrofluoric gas, right? And it shows negative 275.4. So I'm looking under this row, delta G formation of naught, and that's the way you want to see. And here is hydroxide, and it gives you a value, and it gives you value for pretty much all of these guys, right? I mean, there is delta H and S. We will look at those in a moment, but for now, just look at these guys, and you see all of them. Why is it not just G naught? Why is it delta G naught? Because these are in comparison to the when it's at absolute 0, okay? So we look at here, these values could show you what the G naught is at that pressure, 1 atm, and at 25 degrees Celsius. I will go back to that reference sheet in a bit. The standard Gibbs free energy, or G naught, you can utilize a particular equation to solve for that. And we've already seen the first one. That's the Gibbs free energy equation. You take delta G naught equals delta H naught minus T delta S naught. So this naught represents that it's at 1 atm and 25 degrees Celsius. There's another equation which is called the use of the standard free energy formation equation. So that is represented by here. Say the reaction A and B produces C and D. If this is the case, you will take the summation of the product, okay, with the appropriate amount of moles that is in the coefficient, minus the summation of the G naught of the reactant with its appropriate coefficient. Now, I know this is sort of all over the head, so we're going to actually do a practice problem to better illustrate these two ways to calculate the Gibbs free energy. So here's a learning check we can do. Let's go ahead and read it. Calculate the standard Gibbs free energy change for the vaporization of water at room temperature 298 K. So it's already at 298 K, which means it's at standard. What is the computed value for delta G naught? Say about the spontaneity of this process. Report your answers in 3 significant figures. So you see water turning into water gas. And it's saying at 298 K, at that temperature, what is the standard free energy in value, and is it spontaneous or not? So there is definitely two ways and to calculate it. And first of all, it says to calculate the standard Gibbs free energy, but we're going to utilize the formation one, okay? Which one is that one? We're going to use the standard free energy. Yes, we can use this one too, but we're going to use this one first, and we will go over to another learning check that will use both of them and compare the two. So let's use a standard free energy formation for now. So standard formation says that delta G naught is equal to the summation of the coefficient of my product. My product coefficient is 1 because there's only a 1 there, and here's 1. So here's my 1. And the G naught of H2O gas, right? Minus, because that's the only product that's there. If there's more product, I would add more of the G naught. Now here, this one is 1. And then G naught of H2O, not of gas, but of liquid. So what we're going to do is we're going to go back to the reference sheet and see what the water gas and water liquid G naughts are. So if you look, the water H2 liquid and water H2 gas is right here. Okay, please make sure you are looking at the right column. This is delta G naught. So we want to look at the G one, right? So we're here. And also note the unit, kilojoules per mole. So that's important because if you look at entropy, it's just joules and Kelvin mole, right? They're all important. So we're going to take these two values and plug it into our G. Liquid is negative 237.1 and the gas is 228.59. So let me go back. So here we're going to write 1 mole, and the G naught of the gas one was negative 228.59 kilojoules per mole, minus. And then we had our 1 mole, and that, where am I getting that 1 mole? I'm getting it from here. And where am I getting that from? I'm getting it from the coefficient of the balance equation. and that will be negative 237.1 kilojoules per mole. I could cancel out the moles since they're in diagonal each other, and we can calculate this out. Okay, so let's go ahead and calculate this out. It's basically negative 228.59 minus the negative 237.1. Negative 228.59 minus the negative 237.1. Why didn't I multiply it by 1? Because if you multiply it by 1, it's the same value. So I didn't want to put all that in there. And we get 8.51. 8.51 kilojoules, and it's positive. So what does that say for the spontaneous reaction? Is it spontaneous or not? So this would be a non-spontaneous process since it's a positive value, non-spontaneous. Does it kind of make sense? At 25 degrees, will liquid form into gas at 25 degrees? Well, liquid forms into gas. The boiling point of water is 100 degrees Celsius. So 25 is quite low, so it doesn't really want to do that, at least not quite yet. Maybe very teeny bit. And so hence why this is a non-spontaneous reaction.